5.6 Indeterminate Forms and L'Hopital's Rule. Recall that the indeterminate forms because they do not guarantee a limit exists. In the past, we attempted to rewrite the expression by using various algebraic techniques. Okay? So, here are all of the indeterminate and determinate forms for a limit. Okay, so if you, for all of these, let's say you have some limit, we'll call it f of x. As x approaches some number, we'll call it a. So for the first one here, if your result is 0 over 0, this is going to be indeterminate. Okay. Same thing for the next one here. If you get positive infinity divided by positive infinity, or negative infinity divided by negative infinity, or any combination there, that's going to be indeterminate. If you get infinity minus infinity, that would be indeterminate. We could not determine what that actually is. If you get 0 times infinity, indeterminate. 0 to the 0 power, indeterminate. 1 to infinity, which we'll go over because that seems like that should equal 1. Infinity to the 0 power. Determinate forms, if you get infinity plus infinity, that's still going to be infinity, so you can conclude that is the answer. If you get negative infinity minus infinity, you can conclude that that's negative infinity. If you get 0 to the infinity power, that will always be 0. If you get 0 to the negative infinity power, so that would be like 0 over or it would be like 1 over 0 to the infinity power. That's going to equal infinity. And if you get infinity times infinity, that's going to be infinity. All right, so for all the indeterminate forms, we're going to use L'Hopital's rule. We'll go over what that is in a moment. When you actually get the determinant form, when you actually figure out what the answer is, you're done. You don't need to do anything else. So let's do this special case here. Okay, so let's say we have some limit of f of x raised to another power, which is a function g of x, as x goes to some number a. So let's say in this scenario here, when f of x goes to 1, g of x goes to positive infinity. So you get 1 over infinity, which that is indeterminate. We can't conclude what that is. We can't say, oh, that must be equal to 1. That's not always the case. I'm going to show you some examples here. So look at this example below here. Let's say we had the limit of e to the x times, or the limit of e to the x raised to the 5 over x power. Okay? And this is going to equal 1 over infinity, which is actually indeterminate when x approaches 0 coming from the right. Let me show you why. Notice here, if I simplify that, that's going to give me this. Then if I evaluate the limit, that would be e over 5. Okay, so again, if f of x equals e to the x and g of x equals 5 over 8, as f of x goes to 1, sorry, that should be an x, notice that g of x will go to positive infinity. Will approach positive infinity. Okay, so for this case here, when we got 1 over infinity, right, when we evaluated it here, but then when we manipulated it here, we got e to the 5th. Very similar problem here. So look, this problem is exactly the same as the other one. The only difference is I changed the power. I made it 6 over x. Again, when we evaluate this limit as x goes to positive, or x goes to 0 coming from the right, e to the x would be 1, and 6 over a very, very, very small 0 would be infinity. Okay, and then if we tried to manipulate this algebraically, this would be the limit, multiply here, of e to the 6th as x approaches 0 coming from the right. If we evaluate this, this would be e to the 6th. Well, since, notice these are the same, but these are different. That's why it's indeterminate. We can't, anytime you get this, you can't determine what the solution is because it changes depending on what the problem is. All right, so we're going to show you a technique to simplify these limits when you get the indeterminate form. So let's look at this first example here. This would be indeterminate, right? Okay, and in the past we used these algebraic techniques. So we took the limit as x approaches -1. We can't have -1 because that would be undefined. I could factor out a 2 giving me x squared minus 1. And then I could take this limit as x approaches -1. And then I could rewrite this as x minus 1, x plus 1, all over x plus 1. Then here this reduces. So x equals -1. And now we can evaluate this limit using direct substitution. So this would be this is going to be -4. Today we're going to use this technique known as L'Hopital's rule. Okay, so let's say we had this function again, the limit of 2x squared minus 2 all over x plus 1 as x approaches -1. Again, we couldn't evaluate this, okay, because we're going to get a 0 in the denominator. But we can do something interesting here. We can use this L'Hopital's rule, which basically says if you have the limit of some rational function, that's going to be equal to taking the derivative of the numerator and the derivative of the denominator. We're not going to go through the proof of that. I guess we will a little bit here. So this is going to be, if I take the derivative here, this is going to be 4x all over 1 as x approaches -1. Now if we evaluate the limit, this is going to be -4, so same thing. Much easier technique. I'll go through the proof in the next video.